Hello everyone. This is the second worksheet on hypothesis testing, and this focuses just on the critical value approach and finding critical values. All right. Now, the critical value, as you know, is a cutoff. All right. Critical value, let's me write that down. In fact, the critical value is a z value, or if we are doing a t-test, it would be a t value. So z or t. Actually, let me just write the word or instead of using a slash. It's a z or a t value, which is the cutoff between the reject and the do not reject regions. All right. So it's a cutoff point between the reject and do not reject regions. All right. Do not reject regions. I'm going to refer to as the do not reject regions as the DNR. All right. And the z value will correspond to what is called the alpha value. What is that, the alpha value? It's the probability of making a type 1 error, and therefore it represents the area under the curve that falls in the reject region. All right. So the question says, for a two-tailed test with alpha equals 0.10, determine the critical values and then draw a graph that illustrates your answer. Now, what I'm going to do is start with the graph, all right? And then we will find the critical values. So we have our graph, which is a standard normal curve, and we know that under the standard normal curve, we have z values, and the mean, all right, the null hypothesis mean is going to be located at the center. In a two-tailed test, the reject regions will be on both ends of the curve. So we will have a reject region on the left-hand side. We'll have a reject region on the left-hand side and a reject region on the right-hand side as well. Okay. And the region in the center now is going to be the do not reject region. Now, each of these reject regions have an area under the curve, and that area will be determined from alpha value given to us. So here, the alpha value given to us is 0.10. All right, that's the area of the reject regions. However, because we have the reject region split over both ends of the curve, we have to split our alpha value as well. So for a two-tailed test, and only for a two-tailed test, alpha will need to be divided by 2. So we will have alpha is 0.10. Let's put in that value here. 0.10 divided by 2 is 0.05. What that means is the area on each side of the curve for the reject regions is 0.05. It's alpha by 2, right? It's alpha by 2. Same for this one, alpha by 2. And the cutoff values, which are always z values or t values as the case may be, is going to be the z value corresponding to 0.05, this area. On the right hand side, it's going to be z of 0.05. On the left hand side, this cutoff is going to be negative z of 0.05. On the left hand side, all values to the left of 0 are going to be negative. All right. So just remember that on the negative side, your z value should be a negative value. On the right hand side, it'll be a positive value. So now we have to find the exact z value that corresponds to 0.05 on either end. So z of 0.05, but it's going to be a minus value as well as a plus value. We are talking about two z values here. It's going to be the same absolute value, but it's going to have both the negative and the positive sign. So negative, it should be plus minus actually. So it's going to be plus minus z of 0.05. So now we have to either consult our table, or if you have a graphing calculator with a statistical package in it, you can look up the z value over there as well. But I'm going to go to the table, but I'll use today the table for the statistics 2 student, which is this one. Now, for the statistics 2 table, there's a special table provided with special alpha values. All right, so we have this small table here with 1, 2, 3, 4, 5 values for special alpha values is under the T table. All right, so the T table here is table 4. So if you go down on the right hand side, there's a small concise table between table 4 and table 5, and this has special alpha values like 0.10, 0.05, 0.025, 0.01, and 0.005. So look up the z value for 0.05. It's 1.645. So that's going to be our z value. It's going to be plus minus 1.645. That means the cutoff on the right hand side of this figure is 1.645. That's the z value. And on the left hand side, it's negative 1.645. Those are the critical values. So these are the plus minus 1.645 will be our critical value when alpha is 0.10 for a two-tailed test. Okay, critical values. So this was the two-tailed test situation. The next question says a right-tailed test with alpha equals 0.05. Now in a one-tailed test, which is the right-tailed or the left-tailed, you don't have to worry about splitting the alpha into two. All right, it's the reject region is going to be on one side only in a right-tailed, and same in a left-tailed test. So alpha is going to stay intact. So here too, I will start with the diagram first. So I'll do part B first. So we have here our normal curve with the null hypothesis mean here. And it says it's a right-tailed test. That means the reject region is going to be on the right-hand side, correct? The reject region is going to be on the right. And this is the DNR, the do not reject region. The area corresponding to the reject region is here, all right? The area under the curve that corresponds to the reject region. And what is the alpha value we have? The alpha value is 0.05. So the critical value is going to be the z value corresponding to an alpha of 0.05. So z of 0.05. And we just looked up that value is positive 1.645. So I'm going to go back and answer part A now. It says determine the critical values. Critical value for right-tailed test is going to be z of 0.05. You may write one more step here. So it's z of alpha, no alpha by 2, because this is a right-tailed test. So z of alpha, which is in this case z of 0.05, is positive 1.645. And we can write that now in our diagram as well. It's positive. Don't need to write the plus sign. So it's going to be 1.645. All right. Now the last question in this worksheet is for a left tail test with alpha equals 0.01. So this is a different alpha value, but it's a left tail test, which is also one tail test. So only one reject region, but on the left hand side of the curve. So let's draw the curve first. Okay, so the curve is here. Okay, but the reject region now is going to be on the left hand side. So here's our reject, and then our DNR on the left hand side. The area corresponding to the reject region is an alpha value, is alpha of, but it's 0.01. 0.01 is this area. All right, so we are looking for a cutoff which will be right here corresponding to an area of 0.01 to the left. All right, so this is going to be negative z of 0.01. Again, this is on the left hand side. The reject region is on the left hand side, so the z value is also going to be a negative value. Anything that is to the left of the center point is going to be negative, right? So we have to look up our table. I'll go back to our table and just look for z of, where's my table here? Right, so z of 0.01 is right here, but this is a positive value. Make sure we have to make it negative because our cutoff is on the left hand side. So it's going to be negative 2.326. So let's go back. It's going to be negative 2.326. So let's answer part A now. We are looking for z of alpha, but because it's a left tail test, it's going to be negative z of alpha, which is negative z of 0.01, and we looked up our table. That's equal to negative 2.326. So that's how we are going to find the critical values when we use the critical value approach. And then we are going to bring our test statistic and see in which region it falls, and then take a decision accordingly. But we will do all that in the next few worksheets. Okay.